Hi everybody. Today we're going to talk about how to circumvent Qbot loader's anti-debugging techniques and extract the final payload. Qbot is a common banking malware that comes with several anti-reverse engineering techniques, including several layers of packing and then a lot of anti-debugging techniques. In a previous video, we talked about how to unpack the first level to basically get to the Qbot loader, and then in this video we're going to go over how to circumvent the anti-debugging techniques inside that Unpacked Qbot loader, and then finally unpack the final payload so we can identify the IOCs. We're not going to go too deep into the unpacking process because we just did that in the last video. So if you want more in-depth, watch the previous video, how to quickly extract the Qbot loader malware, or how to quickly unpack Qbot loader malware. So for this video, we're going to walk over the general process of how Qbot loader works, at least for the path that it goes down to extract the final payload. And then that will help us determine how to kind of put breakpoints and patch the program. And then we're going to go ahead and demonstrate the techniques. And then we'll finish up by going a little bit more in depth into the anti-debugging techniques, just so you can learn what they're doing for training purposes. So the file we're using is the same file we use for the how to quickly unpack the Qbot loader malware. So the hash is in the description, and you can download it from mouseshow.com. And we're also going to look at a marked up, or at least a partially marked up Ghidra database. And that file is in my GitHub page, and you can download that from the video description also, so you can look at it in more in depth. So let's start with the general process that Qbot loader performs in order to unpack the final payload. And just remember that the Qbot loader has several different command arguments and several different paths. We're only going to focus on the one that you need to go through in order to get to the final payload, because the payload contains all the malicious activity, and we need to be able to extract that in order to extract all the IOCs for the Qbot loader or Qbot malware. So it has a couple steps you can go through. The first thing it's going to do is it's going to execute a copy of itself in a child process with the /c option, and that performs all the anti-debugging checks. That child process is going to return a Boolean result that's going to be stored in a global variable, and that variable is used throughout the program of the Qbot loader to verify that you're not running in a analysis environment. The next step is that you're going to verify the process is running in a correct location, and that location is going to change based on the file name. And then after that, it's going to inject the unpacking stub into a suspended process, just using standard code injection techniques. The final step is that unpacking stub is going to unpack the final payload from the resource sections. So by understanding those steps, we know what we need to look for in the code and then how to basically bypass it. So we're going to have to look at where it stores this Boolean result in the child process global variable, because it's used throughout the program, so we need to patch that out. And then we'll look for the injection into the unpacking stub. And then finally, we'll run through the unpacking stub to extract the payload. Now we're going to do all this manually. Qbot, you could write a configuration extractor, like an automated configuration extractor, but that's not always the best case, and so I want to show the manual method. If you have an automated extractor, it works great when it works. It only takes you a second to run it, and if you get the results, you're good to go. If you're going to do this inside like an AV program, or you can run hundreds of samples or daily samples, that is something you want to spend the time to do. And it's not even all that difficult for Qbot malware. The sample is in the resource section. It's just RC4 encrypted, and then it is compressed. The problem is the compression is a slightly modified unknown algorithm. I had seen a blog site that identified what the modified or what the standard compression algorithm was with a slight modification, but I'm not super familiar with recognizing different compression methods, and so it's one that I can take their word for and probably could go write it, but it's not one I know how to recognize myself. So the reason I like to do it manually, because if you're only working at one sample at a time, or maybe a sample a week, a couple of samples a week, once you have a marked up exemplar, when the actors change the variants, they really change very minimally, and generally the program flow, they don't change. And so usually you go through and change the crypto keys, maybe change the string decryption mechanisms, change the compression algorithms, but the general process flow that we talked about here generally doesn't change because that's a bigger architecture change. So once we know what one sample looks like and we have a marked up database, we can basically use those marked up database in order to look at the variants that are unmarked and find the key locations here. And then we can just, patch the programs we need to go down the right path and we can let the malware perform the decryption and decompression. That means we don't need to spend the time to first find the decompression and decrypting sections and then reverse them to see what the new keys are if they switch out the algorithms. By letting the malware perform those actions on your own, you basically go to the easier task of just identifying locations instead of identifying the algorithms and the crypto keys. So it's, again, if you want to write, if you're going to go through these samples every day, I would spend the time, make an automated extractor. If you're only going to work, a handful a month, it'll take us a couple minutes once you get used to it. Maybe it's a 3 or 5 minute task to extract the payload. And so it's really not worth having to check to see if the mechanisms change, if the crypto constant change, or algorithm, if the key change, if the compression change, and so forth. And on top of that, it's also just a good training methodology of going from one marked up database and looking in a variant to see kind of how it looks similar. With all that being said, let's go ahead and get started. So I already have this in Ghidra, so I'm going to open it up, and I'm going to go to hit G to go, and go to the entry. So the first thing it does is it gets the command line arguments, and then you do this command line argv. You go through a couple initialization functions here, you dynamically load your imports, and then finally you do a check of your number of arguments, so your argc, against EBX, which you can see here is the value 1. So if you're less than or equal to 1, which means you have no command line arguments, you take this green path. So we're going to double click that to follow it. And now you see we have a function inside an if statement, and we store the result of that function into a global variable. So that global variable is our anti-debug results, and that's what we need to patch out. We can't just bypass this step because we need this anti-debug result to be 0. You can see if we hit Control-Shift-F and look at the cross-references, this is used several times throughout the program. Every time it's used, if you don't have the correct value, then your program will know it's being debugged, and it will actually overwrite the running copy with a embedded copy of calc and then delete itself. So we do need to patch that out. After we get through that part, the next step is it generates basically a random string based on the file path name, and that just uses it kind of as a seed. And then you're going to compare your file name to the random generated name. So again, that's something that we could go through and determine for what file name the correct path is going to be. But you never know if variants are going to change that. And so it's just easier to get down to the string compare and let it basically fail and then patch the result to be true. In that case, we would take this green path. So when we double click that, and now we come through here and just go through the first block or two, and you see this compare this global variable to 10. And basically we take that path to the green path where it's not equal, double click it, and then we get through this couple mutex stuff, and then in the code injection into new process. Now we're going through here to how to see it manually, but this part we can actually do a little bit easier than debugger, so don't worry too much about how to find this. But if we go into here, and I'm just going to scroll through here until I find the create process. And we see here we get this create process W with the telltale argument of the 4 that tells us to create it in the suspended state. So that's going to be for your standard kind of process hollowing or code injection techniques. The very next function after the create process is going to be in the inject code stuff. So the important thing is just to know once we find the create process W, we go to the next function and step into it. So go into here, and now we're looking for, this is just using standard code injection techniques. So you're getting the thread context so you can get the address entry point. And then down here, we're going to modify the address entry point to be a jump to this main for injected code. What we're looking for in the debugger is we're looking for this echo 9 and the sub of a register with 5, and then add to that same register with this offset. Echo 9 is the opcode for a relative jump. And then we're subtracting 5 from here because 5 is the length of the relative jump opcodes. You have the instruction. You have the 1 opcode for the relative jump, and then 4 bytes for relative offset. And then we're looking for this add, and that basically does the math calculation to get from the address entry point into this function. So we don't want to actually run this function inside this assembly process, because then we'd have to patch out this main to kind of have an infinite loop and then be able to attach to it, and then it just goes through a bunch of work. So because it's the main for injected code, it basically stands by itself. It's a standalone code. So all we're going to do is actually find this, and then we're going to double click it, and we're going to change our EIP into this function and just let it run and do the standard unpacking techniques from there that we did in the last video. Because this part is just going to scroll through. We're going to do this decrypt and load final payload. So if you go into there, we're going to scroll down a little more. We had this load library manual on decrypted resource. We can get into that one. Load and decrypt resource stuff wrapper. And so let's go into that function. And then here we load and decrypt resource stuff. And then we'll go into it again. And then you can see, so here's an example where we do this anti-debug check. You can see we're doing IMAL with a random value. If this anti-debug result is 1, we're going to get a value here, and it's going to be a random value, which is not what we want. That's why I need to patch out this anti-debug result to be 0. So you can see here we start loading the resources. We do kind of crypto, RC4 stuff. So all that's not too important, so we're not going in depth of how Qbot Loader works. So I'm just going to hit Alt-Left to get back to where we're at. So you can see here was where we're patching out the address entry point for the main for the code injection. So hit Alt-Left again. And once we're done with this process injection stuff, then we've now injected our code into the hollowed out or the suspended process. We patch the address entry point with a jump into the main injected code. And you can see the next thing we do is basically just call resume thread, and that's how we do our code injection. So it's a pretty standard technique. And so, but you can kind of see a slight markup if you want to see what it looks like in more detail. So as you can see, that's a pretty simple process. So I'm going to go ahead and close this out. Now, the sample we're going over, I'm not going to do a variant because I want to show, since we have this hash. So I'm going to open this up in X32 debugger. But I'm going to show you in an unmarked version how to find the location of interest. So I'm going to hit F9 to get in the address entry or the user space. And then I'm going to go into the same file, but this one's an unlabeled file. So G to go and go to entry. And this would work the same as variants. Because the variants, again, that process flow will generally be about the same, with minor variations. So when we come here, we see the command line to argv. We look at the second argument, and that's the local Charlie. That's going to be our argc. So all I'm going to do now is scroll through and see where this gets used. I already have it selected. And I see here, compared to argc, to the value 1. So that means I know where I'm checking my arg count to see if I have no command line arguments. So I take the green path, and then I see the function with the return value stored in global variable. This is the first location, and really the only place we need to put a breakpoint. And so we're going to go, at least a breakpoint where we know the address. So I'm going to go to this 401 Bravo Charlie 0 address. So Control G, 401 Bravo Charlie 0. And then I'm just going to hit F4 to run to here. It'll take it just a second. And then we're going to get the return result. Our EX is going to be a 1. You can see that up here in the register view because we are in a debugging environment. So all I'm going to do is double click it, hit 0, and then I'm just going to simply F8 until I get to the string compare. So you can see our string compare. We're comparing the name demo, so that's our path name, with the path, this SUJJIS. And again, that path name is going to change based on the file name. And so I could go through and just have a hard-coded file name, figure out what the path name is, put in that right location. But then you never know if the variants are going to change that. And you can see, since that's always going to be pretty quickly after finding or doing the anti-debug checks, it's just easier to step up here and see what it does. So I'm just going to F8, and then I see my result is 1. String compare result needed to be a 0 to succeed, so all I do is patch that to be 0. Now I'm on the right path to get into my create process. Now finding that create process is a little more complicated, but luckily I can do it with a simple breakpoint. So all I do is hit Control G, and I click in the window, Control G. I'm going to go to create process W. And I'm just going to put a breakpoint and F9. Now I don't want to put this too early because Qbot Loader actually uses create process for a number of different things. We have it for the child process we created. It also uses it internally as like another kind of obfuscation technique. And so we want to wait till after that string compare so that we know the next create process is going to be for the code injection. So Alt or F2 to take the breakpoint off, and then just Alt F9 to get to the end. And if you see, we scroll up just for verification. I see my argument of a 4, which means I know I'm doing suspended process. So now all I'm going to do is basically F7 into the next call, and now I know I'm into the code injection technique or code injection function. And this step, all I do is look for the echo 9 and the sub 5. So I'm just scrolling through here, and I see here my move with echo 9, and I see the sub 5 on ECX. I select that, and I see an address here, so this is where it's doing the calculation. That means that 415 Bravo 2 is our address entry point for the code injection. Now, luckily, this stands alone, so I don't have to change off like opcodes to have like an infinite loop, let it inject and attach to it. All I'm going to do is hit Control G and go to the address, 415 Bravo 2. And now I can right click and do set new origin here. That changes my EIP. I'm now in the unpacking stub, and it's going to unpack the resources and load it directly. At this point, we're going to do just the general unpacking process we used in the last video. So I'm not going to go over in depth, but in the previous video, I showed this general unpacking process. So the same basic steps you use for a custom unpacker when you map a file state to the memory state. And then we had these, the general unpacking goals and the unpacking tricks. So just a brief review is where we had the file state is the compressed form of the memory state. And knowing what the general process is for mapping the file state to memory state, we're going to put some breakpoints on the heap allocations and watch when the file gets decompressed and then copy from the decompressed file state into the expanded memory state. Let me go ahead and minimize that. If you want those more details, again, just watch that previous video on how to quickly unpack Qbot loader malware. So if we open this up in PEBear, this is just for kind of, again, the brief review, and go to these section headers, you see we have raw address and then virtual address. You see the text section starts at 400 on the raw and 1000 virtual address. That's going to be your typical change for 32-bit malware. Your raw address on the file state is at the 400 hex, and in the expanded memory state, it'll usually be the 1000. Occasionally you'll get, instead of 400, 600, and very occasionally, or much smaller time, you'll get 1000, 1000. But for a good 90, 95%, it's going to be 400 to 1000. That means when we get this unpacked in memory, if we go to basically the 400 hex and we see a bunch of nulls followed by opcodes at 400, we know we're in the file state and we know what to copy out. And by copying out the file state, it means our hash will be the same every time we copy it out for the same variant. If you copy out of the memory state, you're going to go at changes based on where your file was loaded for ASLR. You're going to have to refix up the import address table, and that means your file hash will also change because of that fix up IAT. And that means, since you had to do multiple fix-ups, every time you dump out something from the memory state, you have to go analyze that dumped out file to see if it changed. By dumping out in this raw state, I've made no changes. It hasn't been mapped to memory with ASLR. It is going to be the same every time I dump it out, irregardless of my system. And so that means if I get the same hash from dumping out of a file state, it'll be the same hash for every equal sample, and I don't have to analyze it further if I get the same hash back. Alright, so let's go back into X32 debugger. So all I'm going to do now is put Control G. I'm going to put a breakpoint on virtual alloc. So I'm going to go to kernel base dot virtual alloc. Now, if you remember for the last video, a lot of times I will just put on virtual alloc, but sometimes malware will call kernel base virtual alloc directly, and the kernel 32 virtual alloc actually calls kernel base virtual alloc anyways. And so there's a lot of times I'll just put it directly on kernel base just to save myself some time in case it calls it directly. So I'm just going to F9 until I hit it, and then Alt F9 to get back to the user code. And we see here our return value is 0. That means it failed. If I scroll up here, I can see my virtual alloc. We can't actually see it up here. The reason that it failed is this first argument would have been the preferred image space it tried to load it at. And the fact that it failed just means that image space or that address space was already used up, and it needs to do it at a random address. So I will F9 again, and I hit it my second time, and then Alt F9. And now we can see the virtual alloc, we pass it 0 for the first argument. That tells you to do it at a random address. And we see we have a return result now. So in the hex dump, I'll do Control G, go to EAX. Now I need to see if this is the memory used to decompress the file or to map the file state into memory state. So I'm going to right click the first byte and do a breakpoint. And I'm going to do hardware access on the byte. I'm just going to F9 until I hit that something right. Now see I write an M to it. And now we're going to examine the code around it. Now note that we're not just following a process blindly. We know what the process is, and that lets us interpret each step. So I'm looking here, and I see I copied DL from EAX into this EAX plus ECX. My DL I see here is the 4 delta. and then I can see it's coming from EAX. So I'm going to go in dump 2 and do Control G and go to EAX. And I see my full file here. So now I need to determine, is this, so the fact that I'm copying this from one location to another means this original location is almost certainly the file state, and this copied location is almost certainly the memory state. So but to verify, we can see this starts at address 0048. I'll go down to 448 and just verify it's the start of the text section. So I'm just going to scroll through, and we see a bunch of null padding, and then 448, we see the start of code. So that gives us a good confirmation that we're in the file state, because you really will never see the memory state start at 400 hex. I don't think you'll ever see that. Or at least if you do, it's going to be a very rare occasion. So all we have to do is dump this out and fix it up now. Now, just to note, you may be wondering why you didn't see the memory allocation for the unpacking location, where we basically decompress the file state, because I did mention it's encrypted and compressed. And you do have to allocate new memory to decompress it. And so the reason we didn't get it is that it actually used a heap alloc call instead of a virtual alloc. So virtual alloc is called a solid 90 or 95% of the time in malware to do the basically heap allocation, but you will get that 5 to 10% call heap alloc. So instead of putting breakpoints on everything, I tend just to put breakpoints on virtual alloc because it'll almost always be used in one of these steps. If it didn't work and I got past it and didn't see what I was looking for, then I would start putting breakpoints on additional API calls like heap alloc. But it just saves me a little time and works most of the time. So I find it easier to try it out first, and if it fails, then I'll go through and be more complete. So I'm going to open up Process Hacker and just dump this out. So it's at the 298 and then 0048 address. So I'll go to Process Hacker, and you can see here our Explorer started in the suspended process. That's why it's highlighted gray. I'll double click my running file, and then I'm going to go to 298 address. And then I'll right click and hit save. And I'm just going to call this Payload. I'm just going to call it .dll because I've already analyzed it and I noticed a DLL. If I wasn't sure, sometimes I just pick, sometimes they just call it .bin, whatever you want to do. I'm going to open up in HXD, and first thing that I do is clean up the header. So remember, it started at 0048, so I need to go down to address 48. And we see at 48, we had the start of the MZ header, so I select it and just hit delete to clean it up. I'm going to save that, and then we will open this up in PEBearer and see where we need to truncate the file. So we go to the section header, and we don't want the additional null padding because we copied out the whole memory segment. We want to end where the file is expected to end, so that's identical in every sample, and doesn't depend on how big the last page was allocated or the memory was allocated. So our last section is the relocation, and we're in the file state, so we're going to go to the raw address 2charlie200 plus 1 alpha 00. That means we're going to go to address basically 2C200 plus 1 alpha 00 or 2 delta charlie 00. So go back to HXD, Control G, 2 delta charlie 00. And all I do now is Control Shift N, and I just delete everything off. And now it's the exact size I expect it to be. I hit save. I'll close this down, and now if we reopen this up in PEBearer, we can look at the General tab, and we see this SHA-256, the Bravo F Charlie Charlie 44F. That's going to be the same hash we get every time for this sample, regardless of the system we're running it on. So if we dump this out and get this hash, we know we've already analyzed it, and we don't have to re-extract the indicators of compromise. Now I also already had this open in Ghidra, and I'll just show you to make sure you can tell it's unpacked. But G to go, I'll go to the entry point. And you can see if we scroll through here, so it's not the standard address to entry point code, but we see a create thread here. This will be the starting address, so I double click it. And just having create thread in the address entry point wouldn't be from compiler code. So that, and you can see the graph view here, doesn't really look like library code. But, so this is the actual unpacked Qbot payload, final payload. This does all the malicious activity. So you can close that down. And you can see how simple that is. So just by having the one marked up database that we have at exemplar, I can very easily look at all the variants, those couple locations I need to find. Basically, I need to find the location where we execute the copy of itself and store the result in the Boolean global variable. And then I look for the string compare that immediately follows for the correct location. After that, all I do is breakpoint on the create process, so then code injection, and then finally I go into the function following the create process and look for the telltale signs of modifying the address entry point with the echo 9 opcode to get to jump to the unpacking stub. From there, I unpack it just like every other file. And again, we went over a couple in these videos here so far. So if you want the more in depth, just look at the last video for how to unpack the Qbot loader malware. So the last thing we're going to do today is I'm going to walk over just very briefly what the anti-debugging techniques are, just so you can see them for training purposes. We're not going to go in depth. I'm just going to show you very quickly. So G to go and go to entry. So we're going to go down here where we look for the command line arguments. We load our imports. We check our arguments. Remember, when we run this for anti-debugging, we run with a /c. So that means we take this path. We can see we're searching for the slash. And then first it checks for W. If it's not a W, we'll come over here. We sub EX was 43. You can see right click, convert, and then 43 is a C. So that means if our command line argument is a /c, this will be a 0, and we'll take this green path, and we get to our AntiDebian checks. So double click this, and this has numerous AntiDebian check techniques. So this first one is an anti-VMware check. So I'll double click it, and this uses a pretty standard process of, it uses the in instruction, and then you pass the kind of VMX, and you pass an argument alpha to it, and you compare the output to see if it's VMX. This is going to be basically the instruction works different in VMware than it will inside of a native machine. And so this will tell you if you're in VMware. So Alt left to get back. So that one's an anti-VMware check. The next check is also an anti-VMware check. And it does the same thing, same instruction, the in instruction. But this time we pass a different opcode with the hex 14. And we're looking for a different return value. But again, it just means this in instruction will give you a different result inside a native machine versus a virtualized machine. So Alt left to get back. Now we have a third AntiDebug VM check. And this one, we're going to scroll through and we get our setup DI get class devs. And then what we're looking for is a setup DI enum device information. So this is going to enumerate your devices, and we're going to decrypt some strings and then compare them. This decryption string, I think, is this local 90. They're all stored at the top of this function. All right, so it's, maybe not the local 90. But you can see they're stored in this variable here. And these are all constants inside of how it does decryption. So I'm going to hit the semicolon, and I've already decrypted these. So you can see we're looking for device names that would indicate we're inside of a virtualized environment. We have CW Sandbox, Virtual HD, QEMU, Red Hat Virtual IO, VMware VM Audio, VMware Vistas, and then we have a VBox Video for VirtualBox, VBox Guest. So you can see this is looking for numerous different VMware or VM identifiers inside the device names. So Alt left. Next we have AntiDebug Sandbox check. And this is going to look at the processes here with the nuclear processes, and then it's going to compare your names and what it's comparing them to. We'll look at the decrypted values up here. Go hit semicolon, and we can see this is just looking for general reverse engineering tools or sandbox tools. Process Hacker, a CFF Explorer, Wireshark, IDA process, WinDebug, a bunch of different processes. So it's just looking for sandbox or analysis environment tools. So Alt left to get back. Now we have another sandbox check. This one I think is looking for the module name. We can see we're getting our create tool help 32 snapshot. We're looking at the modules. We're decrypting our strings and then comparing the module names. So if we scroll to the top, we'll check. You can see we're looking at the module names for any modules are SBI DLL or IVM inject. This is for Sandboxy. The IVM, I can't remember what it's for, but just Sandbox processes names it's looking for. So Alt left. Now we have one more Sandbox check. I'll double click it. And this one is looking, again, we're looking for module names, and then we're just doing a comparison on the module names that we're running as. And here we're looking for hard-coded names that sandboxes often use. So we can see sample, malware sample, artifact.exe. just things that for the simpler sandboxes that don't randomize the file name. So I'll alt left to get back there. I have two functions here. I called AntiDebug shell no check. And it's because if you look inside of here, they basically set this up as if you're probably going to use like an exception handler check, but they didn't actually implement the code. So I don't know if that was a mistake. I don't know if they just have it here, the shell, and maybe some variants have it turned on, some have it turned off. But these two functions don't actually do anything. So that's why I called it the no check. And finally, we have this AntiDebug VM check here. So this one, we're using the CPU ID instruction, and we're looking for genuine intel because the string is going to be different on a native system versus a virtualized system. You can see we're doing string compare for that genuine intel. And that's really all there is to it. So this whole AntiDebug check we'll go through. You can have a couple different paths. You can see if we come down here, we can do the same checks again. But those are really all the major checks it's doing. So alt left to get back. And then once it gets back, it'll do the AntiDebug checks, and then it'll return, and then we store off the result in the global variable I saw before. So I really want to stress, so those are just anti-debugging techniques that are pretty simple to identify and pretty common. So it's nothing complicated, but you see how varied they are. And so it's going to be hard to run it in your analysis environment without patching it to get past those. But as you can see, just by having the one marked up template, and this you can download from the GitHub, so you'll get it partially marked up. It's incredibly easy to look for these couple locations you need to patch out inside really any variant of the Qbot loader. And that way you can go through the unpacking process and let the malware unpack the code for it, and then just dump it out of memory inside the file state. And then we can extract the IOCs from there or analyze it for functionality. If we do this in automated configuration extractor, you're going to have to do a lot more work. When it breaks, it's going to take you significantly longer to update the configuration extractor than it will just to unpack a couple of samples. So again, if you need this and you're running through a sample every day, I'd write the configuration extractor. If we're working through a couple of samples a month, sample a week, it's takes you a couple minutes to do this by hand. So it's not worth the effort to write an automated solution. So I hope you enjoyed the video today. If you did, please like the video below and subscribe to my channel so you get notified when new videos come out. I also love to know what you think, so leave me comments below. If you want more reverse engineering tips, follow me on Twitter. And if you're interested in structured stringing, check out my website for the malware analysis classes I offer. Until next time, keep on practicing and try to learn something new every day.